Hello everyone. Today, here in our 13th day of our notes, this is our last and final day in this unit. So again, we're talking about showing triangles are congruent and other pairs of corresponding parts. And so much of this will be similar to the work we've done before, but there are a few extra details to bring up. This very first proof is a warm-up. This is one that I want you to try on your own. Notice that what we're starting off with here is a pair of congruent segments. We have some perpendicular segments, and we also have a midpoint. Here are the two triangles, and we're trying to show that the two triangles are congruent. So there's a few key steps provided in the proof, but pause the video, complete this, take it as far as you can, and then resume the video and see how you did. If we continue on, notice that we really have three ideas that are provided to us in the given statement. We could separate these three ideas on three separate given lines. You could see that the first two are linked together and are put here on statement number 1, and this third idea is put down here on statement number 4. And the reason these are linked together is to save space, really, and this is our first pair of congruent parts, and you can't really take that idea any farther. It is what it is, but we can build off of this idea of perpendicular lines, right? So if ED is perpendicular to segment BD, then we should have a right angle there. Well, if we've marked it, we need to name it. So angle D is a right angle, and we can use a three-letter combination or just a single letter here for naming the angle, as it's the only angle at vertex D. And then similarly, segment AB is perpendicular with that same segment BD, so we have another right angle. So angle B is a right angle. So here's our if-then statement. If perpendicular lines, then they form right angles. So line 3 here is really the tricky part. You might be tempted to say that the two right angles are congruent. So what I have here on this little piece of tracing paper is in fact the wrong way to go. We don't want to say this, but this is a common transition. Sometimes we do want to say that the two angles are congruent, but we don't in this case. And the reason is because you'll notice that here what is given to us is that the hypotenuse has been marked. Not only do we have a right triangle, but we have a hypotenuse that's going to be included. So that suggests the RHL pattern. So if we have the RHL pattern, then R stands for right triangle, which means that the next line has to say that these are right triangles. So triangle ABC and triangle EDC are right triangles. And so we would say if we could say something like if triangles have a right angle, then they are right triangles. Alright, so if triangles have a right angle, then they are right triangles. Now again, the reason why we're not saying that the two right angles are congruent to each other is because that would set up a pattern of side angle side or angle angle side, but actually the markings are such that none of those patterns work. We can't use angle angle side, or we can't use angle side angle, or any of those other possible patterns that we've learned. We have to use the RHL pattern because the hypotenuse is a part that has been marked. So we have, notice, we have the R part of the RHL pattern, and what was given to us is not just any pair of congruent parts, but that's the hypotenuse. So we need the leg, and that's where now the midpoint comes in. If we have a midpoint, then we have two congruent segments on either side of that midpoint. So we would say segment BC is congruent with segment DC. If midpoint, right, so that describes what came before. If a point is a midpoint, then there are two congruent segments. And that then provides the L part of the RHL pattern, and there's our proof. So what we're looking at next, in the next three examples, is we're taking it a bit farther, and that's introduced here in this line at the top. It says, you should realize that proofs can stop at congruent triangles, which is what we had just done in the warm-up, or we can go further to prove an additional corresponding parts are congruent. That's what we had done in the previous day of notes in day 12. Or, and this is what we'll do today, we can go even farther, as you will see below. So if you take a look at the left-hand side, you'll notice that right here on line 5, that's where the two triangles are congruent. So up to this point, it's the same kind of work as what we've been doing so far. We're trying to find those three pairs of congruent parts so that we can then show that the triangles are congruent. And then yesterday, in the previous day of notes, we went one step farther by showing a pair of parts as congruent. So what's really new today is we're building off of that and going one farther step by saying, well, if these two parts are congruent, is there some other implication that we can know? So let's see what we have and what our goal is. Here's the two triangles. We see that we have some perpendicular segments, and we have a congruent segment. So again, if we have some perpendicular segments, all of that could be put together on one given line. There it is. Here we have a pair of congruent segments. That could be put on a separate line, but we just put it all on line 1 here anyway, just to save space. So there is our start. You can see that things have already been marked. And so if we have perpendicular segments, we have right angles. If you mark it, you have to name it. And so that's what we did here on line 2. So if perpendicular lines, then they form right angles. Alright, now we're taking a look at these two angles, and we are setting them congruent to each other. Right? So if angles are right angles, then they are congruent. Now pause for a moment and notice the difference between this example and the one we did at the top of the page. You'll notice in the previous problem, the warm-up, here in line 2, we also have right angles. We said angle D is a right angle B is a right angle, and here we did not say those angles were congruent. We went in the different direction of saying we have right triangles because we recognized that the hypotenuse was marked, and that would set us up for the RHL pattern. So now consider that in our current example. Here on line 2, I have right angles. Now, you'll notice we're not saying that we have right triangles. Because the hypotenuse is not marked, we're not going towards the RHL pattern. That means we don't want to talk about the hypotenuse, and we don't want to talk about a right triangle. That means we're not using the RHL pattern. We need some other pattern like a side angle side or angle side angle, something like that. And so that's why we're setting the two angles congruent to each other, and we're not saying that we have right triangles. Alright, so now we bring in another pair of congruent parts. Angle ACB is congruent with angle ECD. Remember, don't just call them angle C. You need a 3-letter combination. These are vertical angles. So if angles are vertical angles, then they are congruent. So keeping track of what we have so far, at the top on line 1, that was our first pair of congruent parts. Here on line 3, that was our second pair of congruent parts. Here on line 4, that's our third pair. Again, once you find all 3, that's when you can now say that we have enough information to show that triangles are congruent. So we need to know what is that pattern. So we take a look at one of our triangles, and we notice that we have 2 angles that are marked. We have one side that is marked. The side that is marked is between the 2 angles, so this is an angle, side, angle pattern. Again, notice it is not RHL, because even though we do have a right triangle, we don't have the hypotenuse marked, so we cannot use the RHL. There is no hypotenuse given us here. So that's the basic process of getting to the congruent triangles. Now we have to go a little bit farther. What we're trying to show is that C is the midpoint of segment AE. There's point C. There's segment AE. It certainly looks like C is in the middle, but C is only a midpoint if these 2 segments on either side are congruent. But they haven't been marked. They are the hypotenuse, but we haven't been using those sides up to this point in the proof. We've only been using certain sides and certain angles. So if we want to show C as a midpoint, we first must determine that these 2 segments on either side of point C are congruent. We obviously have that marked here on line 6. How do we know that these segments are congruent? Because they are sitting on triangles that are identical to each other. Right? So if triangles are congruent, then corresponding parts are congruent. Right, so if triangles are congruent, then corresponding parts are congruent. Well, yes, the triangles are congruent. That means all of those corresponding parts are congruent, but we're just focusing on these 2. So now we know that these segments from A to C and E to C are congruent. And if those are congruent, that means that point C has to be smack dab in the middle between them. So let's build our if-then statement here. So if 2 congruent segments with a point between then the point is a midpoint. Alright, so again, notice that the if part describes what came before. If 2 congruent segments. We do have to add a little extra detail about that point in the middle, because if we just say if 2 congruent segments, well, 2 congruent segments could be placed anywhere. We want a very specific kind of 2 congruent segments. We want 2 congruent segments that really came from one segment originally. So if 2 congruent segments with a point between them is my way of saying, hey, we've got this original segment and it's been divided into 2 congruent segments. And so that point between them, in fact, is a midpoint. All right? That's actually the definition of a midpoint, just the other way around. So it would be much shorter to just say definition of midpoint if you're comfortable using that. All right, so there's our first example where we take our congruent triangles a couple steps farther along. So let's see if we can do that now in these next few examples. So if you'll flip over to the next side, let's take a look at what we have here as example 2. You'll notice here that on this figure we have this diagonal, and we've already numbered off these angles 1, 2, 3, 4, just to make it a little bit easier to name those angles, because we'll be doing a lot of work in this proof with the angles. And so we're starting off by saying that segment AB is parallel to segment DC, the top with the bottom. There's no markings there, so let's add those in. Now remember, this is very important. Parallel lines, or parallel segments in this case, does not automatically make them also congruent. This is a separate characteristic, that these are congruent. So we do need to put the tick marks on there. So again, the fact that they're parallel does not make them congruent. These are 2 different qualities. and the segments happen to have both of them. So let's put that here in line 1. Segment AB is parallel with segment DC, and segment AB is congruent with segment DC. Now, you can see where we're headed. We're talking about angles 2 and 4 are congruent. The reason is, or the question rather, is why? How do we know they are congruent? Let's see where they are in the diagram. How do we know that 2 must be congruent with 4? Do you see why? Remember, anytime you have parallel lines, that's a dead giveaway that we want you to find an angle pair, because we've learned if parallel lines are cut by a transversal, then alternate interior angles are congruent, and that's our reason. If parallel lines, then, again, be very careful. Don't just say angles are congruent. You have to name what kind they are. Alternate interior angles are congruent. Here on line 3, we're looking at the reflexive property, so that's talking about the shared side. So mark that. I'll use a double tick mark. This is segment DB. So segment DB is congruent with segment DB. And I'm just going to do a count. Let's see what we have so far. Here is our first pair of congruent parts. Here's our second pair. Here's our third pair of congruent parts. We've got all 3 parts. So now we know we can look to see that the triangles are congruent. So here I have triangle ABD congruent with triangle, let's see, I said triangle ABD. I need to clean that up. That should be a letter D there. Triangle ABD is congruent with triangle CDB. And there's our side angle side pattern. So if you look at one of those triangles, again, you have to ignore the arrow for the parallel lines. You're looking at just the tick marks. There's 2 sides that are marked, the angle between them, so side angle side is what we're looking at. That's now showing the 2 triangles are congruent. So now that they're congruent, let's see, what are we trying to show here? We're trying to prove that segment AD on the left is parallel with that on the right. So we're not talking about if they're congruent or not. We're just talking about, are they parallel? Well, we know parallel lines form congruent angles. Alternate interior angles are congruent. So if I need to show that the left side is parallel with the right side, then I need another angle pair. Can you find an angle pair that is touching the left side and touching the right side? Yeah, that's angles 1 and 3. How do we know that they are congruent? Because they are in corresponding locations on identical triangles. So if triangles are congruent, then corresponding parts are congruent. If triangles are congruent, then corresponding parts are congruent. Notice we cannot use that same reasoning for line 6, because on line 6 we're not talking about sides being congruent. We're talking about sides being parallel. How do we know that the left side is parallel with the right side? Well, if these alternate interior angles at 1 and 3 are congruent, then that means the lines they form must be parallel. This is the original theorem, but backwards. We're going to take this alternate interior angles theorem and switch it around and make it the converse. So here's the if part. The if part describes what came before, which is on line 5. These are alternate interior angles. So if alternate interior angles are congruent, then we have parallel lines. So notice that what we're talking about here is the alternate interior angles converse, which is the backward statement of what we saw up here in line 2. Line 2, that's the theorem, and this is the converse. Okay, so there's an example where we Notice we really do have a parallelogram, because by the time we were done, we figured out the top is parallel with the bottom, the left side is parallel with the right side. So we do have a parallelogram. In our next unit, we're going to be talking more about qualities and properties of parallelograms. The reason why we like them to be introduced here is because we can create these two triangles. We can show that the two triangles inside the parallelogram are congruent. And we'll use some of those ideas in our next unit as well. So we're continuing that with the next example. Here, let's prove the diagonals of a rhombus bisect opposite angles. Again, we haven't officially talked about a rhombus and its qualities, but we're introducing it here because we have these triangles, right? You draw the diagonals and you get these triangles, which means we should be able to show that the triangles are congruent. So let's see what it is they're asking us to do. Prove that the diagonals of a rhombus bisect opposite angles. So when we say opposite angles, we mean the opposite angles like F and H. Those are opposite angles. What we're saying is that this diagonal that goes from F to H is bisecting the angle at F. So this top angle should be the same size as this lower angle here. And at H, the top angle should be the same size as this lower angle. The same holds up with this diagonal at E to G. The opposite angles are at E and G. These are opposite of each other, so those are opposite angles. This diagonal is going to bisect, meaning cut in half the big angle at G. So you have an angle on the right, angle on the left, that should be congruent. Same up here at E, the angle on the right and the angle on the left should be congruent. That's what we're going to show here. So that's what it says here. We're looking specifically at this diagonal from F to H. Instead of using both diagonals, we're just going to look at one of them. Let's show that this diagonal from F to H bisects angle EHG, meaning take this large angle and chop it in half. We want to show that. Take this large angle at F and chop it in half. Let's show that these two are in fact the same size. So we're starting off by saying that segment EF is congruent to FG, which is congruent to GH, which is congruent to HE. That's what a rhombus is. A rhombus is a parallelogram that has 4 congruent sides. Now a square also has 4 congruent sides, but it has more information with 4 right angles. A rhombus is not talking about the angles. A rhombus just talks about the sides. We've got 4 congruent sides. So take a moment and jot all that given information here on line 1. Segment EF is congruent with segment FG, which in turn is congruent with segment GH, which in turn is congruent to segment HE. Now, because there are 2 diagonals in that rhombus, but we're only really talking about one of the diagonals, then what we're going to do is highlight that and use that diagonal as a way of creating our 2 triangles. Because remember, we have to show that 2 triangles are congruent. So we're going to use this triangle, that is triangle EFH, and then this triangle, which is triangle FGH. Those are the 2 triangles. And it'll also help us out a bit if we can number off these angles. So let's number here at angle H, let's call this angle 1, call this angle 2 right below that. Up here at angle F, let's call this angle 3 and angle 4. Since we have to show that these angles are congruent, I think it will help if we just kind of number them off like this. So we can see that we already have essentially 1 and 2 pairs of corresponding parts that are congruent. Now, of course, we have 3 congruent symbols because we're linking all the sides together. But if you look at the triangle, you can see that these 2 sides are corresponding parts and congruent. These 2 sides are corresponding parts and congruent. These sides are also congruent, so put your tick mark there. That's our reflexive property. Reflexive property of congruency, POC. And so that is our 3rd pair of congruent parts, which means we have a side, side, side pattern. Alright, so we're showing that triangle HEF is congruent with triangle HGF. Here there's actually a couple ways we could name the order of the letters, because with the rhombus we have lots of sides that are congruent. This is our side, side, side pattern. Alright, so again, that's step one. Show that the triangles are congruent. We have 3 pairs of congruent parts. Now what we're trying to show is that this segment FH is going to bisect the big angle at H and bisect the big angle at F. We're trying to show that it is bisecting. Well, if it is bisecting, that means these angles must be congruent. So, is that true? Do we know that angle 1 is congruent with angle 2? Do we know that? We do. Why? Because if the 2 triangles are congruent, then the corresponding parts are congruent as well. So we want to say angle 1 is congruent with angle 2. Why? Because those are corresponding parts. And we could also say that for 3 and 4. Angle 3 is congruent with angle 4 for the same reason. So now that we know that 1 and 2 are congruent, that means this segment FH must be a bisector. And because we know that angle 3 and angle 4 are congruent, then again we know that segment FH must be a bisector. So if these adjacent angles are congruent, so again notice we're not just saying if angles are congruent, because if angles are congruent we could be talking about this pattern where we had alternate interior angles. No, we don't want alternate interior angles, we want adjacent angles. If adjacent angles are congruent, then there is an angle bisector. And that completes the proof.